Okay, well, as I said, I'm Charlene DiMeglio, and the thesis I'm defending today is Fear Feedback Loop, Creative and Dynamic Fear Experiences Driven by User Emotion. That's really long. The original idea was procedural fear, which doesn't tell you much either. Everyone was asking me, what do you mean by that? What does that mean? I didn't know either. I just wanted to procedurally inflict fear on people. And then the next day, I got the idea for genetic algorithm, and I started freaking out about fear machines. So yeah, but really what this is, so a feedback loop is something essentially where the user views media, the user interacts with the media. This interaction gets communicated to the computer in some way. The computer then manipulates the media and plays it back to the user, and this cycle repeats for however long. Again, I wanted the system to be driven by user emotion. So I chose fear because conceptually, if you think about it, if I asked all of you, can you think of a happy image? Pretty sure everyone would think of something different. But if I asked you, think of a fearful image, there will be common motifs between people at least. You might think of, some people might think of a snake or a spider, but it's similar. So conceptually, it was easy to pick fear. And I wanted the system to be creative and dynamic. So I wanted the outputs to not be just a selection of predetermined choices or a selection of a continuum of choices. I wanted it to be completely creative. So my hypothesis was, can one create unique fear experiences per user? Meaning, if you view my material and another person views the material, they should morph differently, based on the person's unique aspects. So in order to prove this, I first need to prove that I could detect fear in the first place, because that would be very helpful, and that I could make content scarier. So, but why do all this? So I wanted to make computer and human interactions more meaningful. Right now, a lot of it is preference learning, which is kind of a 2D sort of thing. It doesn't have much depth. It's basically how frequently and based on user inputted ratings. Oh, this was 5 stars. This was 3 stars. It doesn't really take into account of the user's mental state. So if you think about it, if I'm viewing this movie while I'm sad, well, probably will have a different opinion about it than when I'm viewing it when I'm happy. So kind of depthening that interaction. So an example of that would be customization of products and media. So for products, user testing, you have people rate your products. If you can detect how the emotions affect, how their emotions are changing based on the product, you can have automatic ratings where you don't actually have to ask them, you already know, and can deal with the product thusly. Media, easy application to think about it would be like video games, custom fitting video games to people. I, for one, ironically, cannot deal with scary things. So if you create an application that would adjust how scary something is per person, or adjust what is scaring a person based on their interactions, that could be a fruitful avenue. Other applications include medical and therapeutic. This, again, needs a lot more research, but conceptually, if you can create something that produces fears for individuals, you can use it to diagnose and to treat different disorders possibly. So let's say I have a phobia and I don't know of what it is. If you can draw that out of a person, that could be helpful. So also another reason why you would want to do this is expand effective computing in itself. Effective computing, again, if you're not familiar with the term, is computing dealing with emotions. Fear was not seen very much. In my prior research, there was not much about fear. Most of it was done on stress while taking tests, and a lot on road rage, which I thought was funny. So most things are either road rage or that. And the applications that derive from this emotion, a lot of the creative experiences are lacking. For instance, in my prior research, it was mostly focusing on detection. So can I detect emotions, and can I create general models for emotion? So this is my general model for fear. This is how everyone experiences fear, which is different from my point of view. What I'm trying to accomplish, I'm trying to create individual models for every person so that everyone has their own individual model. But every most of the applications stopped right at detection. There was a wide variety of detection ways, like it ranged from anywhere from speech to temperature of the human body. I used EEG and heart rate. Heart rate is important in an application called Nevermind. Nevermind is a video game. It was on Kickstarter a couple of years ago, where you wore a heart rate belt, and based on your heart rate, it figured out how afraid you were, and based on how afraid you were, it adjusted the difficulty of the game. The more afraid, the more it penalized you and made the game harder, which not very doesn't sound too fun to me. It sounds horrible, but it was trying to train you to stay calm in fearful situations. But the difference between this and mine is the concept of difficulty of a game is predetermined. You know, if you conceptualize, a basic game, enemies move faster, something occurs that you know is predetermined. Where the output of, my media, I have no clue what's going to occur, and it should be, completely different per person. Another application that was close to what I'm trying to achieve here was the effective mirror. What this was, users would view a digital reflection of themselves, and the more they interacted and laughed at the image, the more it turned into this funhouse design, which they didn't really specify how they created that funhouse pattern, but it could have been just, a radial, a continuum of this is more stretched out, this is less, but it's similar in the fact that it is a feedback loop. The more the person laughed, the more it distorted, which in turn supposedly caused the person to laugh more, and so on. Another application that a lot of people were coming up to me about was the Google Deep Dream, which it actually came out pretty recently. Google Deep Dream is an application that uses neural networks that are trained on a specific concept, let's say bananas, and points it at an image, and you say to the application, okay, accentuate all the banana-like qualities of this image. And so if you have static noise as your image, eventually bananas start appearing out of nothing. And so how this relates to mine is I'm also trying to focus on a concept, but whereas theirs is a concrete concept like bananas or dogs, mine is an abstract concept like fear. They use a neural network for theirs, and I use a genetic algorithm, which kind of brings me on the how of this whole thing. So this slide will appear in a couple times, so you don't have to take it in all at once. But what you can get out of it right now is the application is formed in 2 stages. The first stage is a model building stage where we create the fear model for each person, meaning we kind of assess exactly what it means for that person to be afraid. And the second part, that's when we create the media and it interacts with the outputs of the model. So in the first stage, when we're trying to create this model, I had users, subjects, view a variety of clips. These clips were taken from online listings of the top scary films, and also as well as ones indicated by other papers. The clips range from anywhere between 30 seconds, about 2 minutes. They were edited in such a way that context was provided without being too long. And we aimed for to try to make it at least just one scary portion per clip, try to not make it too complicated. Users were asked to check which ones they've seen, and those would be removed from the pool of clips. And so we asked them to view it, and after they view this, while wearing the different modalities, which I'll get into later, they would rate how scary it was from a 0 to 5 scale, 0 meaning it's paint drying, it's really not scary, to 5, which is full-on, oh my god, panic. And then also they would pinpoint the exact time in which they felt that emotion, which I used then in the pre-processing of their data to kind of shave down the data so I don't have to deal with 2 minutes of EEG data, which is like a gig worth of data. 15 minutes was selected because often it was specified 5 seconds would be too long, and anything longer than that was unwieldy. And so after that, after every clip, there was a calm period where I showed a neutral image. So after that point, the pre-processing occurred where I gathered from the data gathered from, we have this EEG headset, which sat on the person's head reading brainwaves. There's 14 different lines from that. The pulse oximeter, which, where did that go? Clips onto the finger, like so, as you can see in the picture. I intended to use GSR, which is basically skin conductance. However, unfortunately, the reader decided not to work about 70% of the time. So I ended up throwing it out, although it was a very promising modality and made me very sad that I couldn't use it. It got left out. And so there are 14 different data sets coming from the EEG, and then 2 coming from the oximeter. And from each of those different data lines, I did mean, standard deviation, such as the top 6 are known as the Pickard parameters. They're well known in effective computing, and the bottom 2 were the additional ones I included from another paper. These were for general emotion sensing, not specifically fear, so I wanted to cast my net a little wide. Doing this created 128 different features, which is quite a lot if you only have 10 samples. So I went ahead and ran PCA, principal component analysis, on that to create from 128 to 10 features, and then fed it into my support vector regression, which used a radial basis function kernel, which outputted a fear score. So later on I'll show you how well the regression worked. I used a leave one out validation. I had to duplicate the data in order to do this, because as soon as I removed one, data got skewed. So yeah. Then stage 2. So that fear, the output from that regression was the fear rating, trying to match the user's fear rating to what was found in the data. In stage 2, the fear eliciting material came from this face, which came from a database from Binghamton. This face is not exactly the original content. I scrubbed it of the facial features first and then reapplied the facial features. My artistic ability lacking. But so what essentially happens is that this face is basically used in a bunch of different ways. The genetic algorithm operates on it and creates things like that, where the different facial features get moved around. I'll get more on that later. So each user is given the same 9 randomly generated variations, as well as the base face, to sort of be as a kind of guide the genetic algorithm from going too off the deep end. The fear scores from the regression dictate which faces get to pass on genes. I'll get more into how the genetic algorithm works later on. And 5 generations were run per subject. So the faces were broken down into eyebrows, left eye, right eye, nose, lower lip, lower jaw, and upper lip. They all have the ability to be squashed, stretched, and repositioned. The only interesting one that was different was if I moved the lower jaw, I did a really crude manipulation of it such that it looked like a jaw almost. Basically just adding black to create sort of this crude mouth opening. The implementation is done in Java. It's all object-oriented, and when you need to propagate, these objects are translated into binary, kind of like the binary is akin to the DNA, if you're familiar with more biological terms. Here is an example of a nose. So the first 4 digits is the ID that says this is in fact a nose. The next 2 sets of 10 are the X and Y position. The next 2 sets of 8 are the X and Y scale, done in a sort of percentage, after which, so that gets converted back into a decimal form and then divided by 100 to determine how much. And then the image selector determines some of the facial features had an option of masking. Here the nose is masked out in blue, such that upon rendering the blue would be left out. This kind of gave more variety. Some nose versions were more blocky, whereas other ones had more of this finessed look. This crude finesse. To be noted, the facial features were bounded to the face, so it didn't, just kind of start going off into space, as well as the lips were kept to the lower half to try to keep it a semblance of a face. The intent was to try to make a scary face, not just a blob. So, the genetic algorithm, basically the top scoring individuals would be allowed, top 4 scoring rather, would be allowed to breed. There was 2 different breeding methods, I'll get into that later. And then there would be a 10% chance of mutation, and the face would get validated, which meaning there's not an eye existing out of the plane of the actual picture, it's all within the space. Because the mutation, which I'll get into later, could cause weird things to happen like that. And as well as there are random faces added into every generation to try to provide more genetic variety, just in case a local maximum is reached and it's not as scary as it could be. So,
excuse me? The last slide, is that supposed to be an example of an entire member of the population in the previous slide? Or do you just string those together for all the different parts of the face and that's an entire?
So this is an example of a chromosome.
Okay.
Does that make sense? So this is just, every face is an array of chromosomes, facial features. Yeah. So the population itself consists of individuals of faces which are made up of each of these chromosomes. So there were 4 different genetic algorithm types. The first one picked the top 4 unique scores. This was actually a programming error, but a happy one because it ended up being the most successful. So instead of, if there was 2 5s, it only picked the first 5, which left room for a 4 and a 3 to show up. And it introduced 1 random individual every population. Populations were always of size 10. So 9 individuals would be produced from this, and then 1 random added to every successive population. There will be a diagram explaining this more next up. The next one did a similar thing, except it chose the top true 4. That was after I found the bug. And then the next one chose the top 4, but instead had 4 random ones introduced. So to give you more an idea of what I'm trying to say here, it is the ones that only had 1 random person introduced, the highest scoring individual got to breed twice with every other individual, and then all the other individuals bred with each other. Whereas the one that had 4 random individuals introduced, everyone bred with each other equally, and then 4 were introduced. So that produced the next generation. Before these individuals were added and the next generation was sown, there was options of mutations, and these were fun. There were 4 different mutations. A facial feature could be added, which you see here, removed, or in the actual binary itself, a 0 or 1 could be added or removed. I think the one on the left here was the most interesting. I actually had to call someone over because it was kind of trippy. What happened here was either a 0 or 1 was added or removed, which caused that lip up there is actually probably was originally an eye, and it mutated into a lip because I know I bounded lips to be only on the lower half of the face, and so this one is clearly smack in the middle of the forehead. So that's an example of a mutation, whereas this one is a complete duplication of a whole facial feature, duplication of a chromosome. So just to review before we move on, stage 1, train the fear models. Basically, we had users look at the scary films, and then from there we could train our regression. And then in stage 2, we showed a base of 10 faces, which then got rated, and then the rating, which came from the regression, was fed back into the genetic algorithm, which then in turn affects the media again. So we have this now whole loop going. So back to our hypothesis. The first one we needed to actually validate is, can we in fact detect fear levels? Now, detection of fear levels did not need to be exact. I didn't care if you were specifically 2.5 scared. It needed to just be relative. This face was scarier than this face. It's what we were shooting for. 4 individuals went through this portion of the testing. here you see a blue line. The blue line indicates the rating they gave for the movies. For instance, let's say this one right here was given a score of 1. This person said, okay, this film clip scared me 1. The red line is what was predicted from the regression using the leave one out validation, which, as you see, fit pretty well. The other two set was not as form-fitting, but still gave relatively good results. To go back to the first two, if you notice this kind of lateral green line, that is what occurred when the users viewed the faces. Now, this was not the result intended. We hoped that the faces all would give something different. However, the exact same number came up for every person, which was unfortunate. It's not what we wanted. This could be attributed to not clean enough data or not strong enough elicitors. We were using static images where the regression was trained on data gathered while some subjects were viewing videos. So I'll explain more on that later in the future work, but something that was interesting, though, that came from this is that these two individuals, if you notice, their flat line kind of centers around 1, whereas the next two individuals, their flat round line centered around 3. This tells us two things. One is that the faces actually meant something to people. It wasn't just 0, like, it's better than calm. Another thing is that these two individuals are definitely different, and the individuals who gave these scores self-volunteered that they had mood disorders, which was interesting. It's an observation. It doesn't really prove anything at this point, but does kind of give further research possibilities. So whether or not that caused it to be higher, or it's simply that these people just happened to react more.
Can you go back to the previous slide? Yeah, I was wondering if you see their rating is always 3 or below, whereas the other two subjects' rating is 5. Maybe if you
So
maybe they have this thing to get more scared when they watch.
Yeah, so basically that's one theory, is that people with mood disorders or just these particular people in general, that didn't make sense, but those particular people were reacting more strongly, and that's why the baseline was moved up in that way. More testing needs to be done. These are only 4 data points. So with that being said, how would you then prove that your content's going to get scarier if the regression just says they're all the same? So we went ahead and said, okay, well, let's move away from the EEG data and have them rate them themselves. That way we could at least try to validate the second half of the hypothesis, although we did validate that we can detect fear levels, but for some reason the faces aren't providing a variety of responses. So instead we asked them to, again, rate it from 0 to 5 scale and see if this caused any changes. So these are the faces that were produced using the genetic algorithm that chose the top 4 unique scores. So those are 2 examples. What was interesting about this was one of the individuals noted, these were like yin and yang ones. One individual noted that less eyes made them more scary, while the other one noted that more eyes made things scary, which was interesting. So this graph basically shows the change of the average score over the several generations. We found that there was an 82% change and a 41% change, respectively, between the 2 individuals from their generation 1 to their generation 5. So that those numbers are the average, the change in the average between Gen 1 and Gen 5 for each person. I did a t-test on this to see if it was significant, and I could say with 97% confidence that this was a significant change, which was great. The next one shown, these use the genetic algorithm that chose the true top 4 and introduced 1 random for every generation. These showed a 27% and 25% increase respectively. ID 14, which is the red line, I did a t-test on that, and I could say with 98% confidence that there was a definite increase between the average score of generation 1 and generation 5. However, IDs 3, when I did the t-test, did not provide a p-value under 0.05, so I could not reject null hypothesis that the increase was significant from the average of the first generation to the fifth generation. But that was only one individual out of the set. These last two were the ones that had possibly more genetic variety introduced in them, since they had the 4 randoms introduced. This saw a 33% and a 19% increase respectively, and those both were significant changes with a 96% confidence level. So on average, I went ahead and took everyone's generation 1 data and everyone's generation 5 data and then ran another t-test on it. The average for generation 1 for everyone was about a 1.2, whereas in the generation 5 was about a 2.5, which is over 100% increase, which I could say with 99.8% certainty that matters. It's significantly increasing. One thing to be noted, though, is that these scores were noted by many of the individuals not to be something indicative of their fear levels, but rather how creeped out they were. This, again, is the media that was chosen. This media is static. But we have shown that we can increase the level of emotion for a user, even if it's not the particular brand of fear we wanted. But we can say with some confidence that we can make content scary. So now that we have those two hypotheses proved within some reasonable doubt, I went on to try to prove that the faces themselves were unique, that the experiences created for each of these users was in fact different. I did this. I paired each of the faces up that came from different genetic algorithm varieties so that I can compare them. The reason I did that was if they came from the same genetic algorithm, they should have the same probability of being very similar. Didn't want to cheat and say, okay, I used 2 different genetic algorithms, ta-da. So I compared those 2 faces. The way I did this was I took the facial features, blew them out, and then overlaid them, and tried to see the increase in blue pixels. This method accounted for positioning as well as scale, and that's why I used it. So if you take these 2 and overlay them, they look like that. And so I measured the amount of blue pixels, and then I looked at the one that had the smallest amount of blue pixels first, and compared that to the ANDed image amount of blue pixels. So we went from 27,000 to 74,000. Quite an increase. These are 2 very different pictures, and this is significant. I did a paired t-test, so all of these were considered together, and it was significant. Again, these 2 were taken together and then overlaid. This was a little less of an increase, but was proven to be significant as well. It went from 60,000 to 100,000 blue pixels. So definitely an increase there as well. And this last set that came from the the genetic algorithm that introduced 4 random individuals each generation, overlaid them. It went from a 45,000 to a 95,000 blue pixels, which means that the ANDed image is significantly different than the 2 individuals. So, given that, the hypotheses were met within reason. Fear was detected with relative accuracy. We saw a significant increase in the subject's fear rating, or creepy rating, and the faces were unique per subject. So that was exciting. But still a lot of work to be done. It's not an end-to-end system, and it's not online. I had to do a lot of, behind-the-scenes editing of data. The modalities were running on different software. The software was not orchestrated together, so I had to do a lot of syncing of timestamps and things like that. It was difficult to hard code that for the first one, since everyone indicated a different timestamp when they decided to be scared. For the second half, I was able to hard code it since the faces were shown in a certain pattern. Faces were shown such that I knew, okay, after so many neutral images that this would show up. So creating this end-to-end system as an online system is another step. Also creating it such that the 2 hypotheses that were met, they can help each other maybe, such that the EEG data does in fact feed into the genetic algorithm and make a difference. We can do that by cleaning the data. Left the data relatively unclean because I wanted to sense any sort of difference. I wasn't focusing specifically on which EEG channels were going to make a difference. I just wanted a difference. Cleaning the data may help. It's unknown. Also, a stronger generative engine. If you remember, the regression was trained on movies. These have sound, motion, and context. Sound was actually a stretch goal for this, but was not accomplished. Motion is another thing that could be easily achievable from the genetic algorithm. These two things are definitely something I'm going to work on a side project later on, working on my generative engine. Context, which is something that was definitely available to those viewing the movie clips, is not something you can generally generate procedurally, but you can provide that by integrating it into other projects. So once this becomes an end-to-end system, you can integrate this into perhaps a video game where you gauge people's fear by actually showing them scary scenes in the beginning and then morph things later on. And so you provide that context, that storyline, which engages the user and gives them more investment in the actual media. Another avenue of future work is the psychological aspect of this. That note that I found while viewing this kind of sparked some ideas on how to use this for psychological studies, seeing if you can diagnose or different mood disorders and things like that. It's unknown if this is even useful for this. It's just 2 data points, but it's definitely an avenue for future work. But yeah, definitely we'll be working on this in the future. But yeah, any questions?
I'm sorry, I'm not 100% clear. So you talked about the movie clips at the beginning, and then you talked about how you trained the genetic algorithm on the different facial features and how it adapts over time to make them more scary. How did the movies have a direct connection to that, or were they like a separate part of your project?
So they would have. So the movies trained the regression. The regression was supposed to output fear ratings that would be used by the genetic algorithm as a fitness function.
Mm-hmm.
However, for some reason, the faces that were being produced provided one. So the trained regression that was trained on the movies, when the data that was gathered while viewing the faces was fed into the regression,
mm-hmm.
it outputted the same number for every face.
Okay.
So I had to leave that behind to try to validate the rest of the experiment.
Okay.
Does that make sense?
Yeah, kind of.
Any other questions?
Did you do any sort of filtering the raw EEG data for generating features from it in terms of noise?
No, didn't. Did not.
Just a thought in my head, and I know this is hard to do, but I wonder if the sharp edges in these images made it look more edited than real, and therefore maybe people didn't get as afraid.
Yeah, that's definitely possibilities. If I could have went back and someone told me later on, they're like, you should have used the PNG because you could have did alpha levels and all these things. I didn't know at the time when I did it, but there's definitely things that could be added and removed from this. But something that could be gained from this is such a janky generative engine can produce a difference. It's exciting because if it was really actually something that wasn't so cut and paste, what would that what type of change would you see there? It's definitely something exciting, something I'll work on later.
Now, you mentioned that these images are rated as creepy versus scary. Can you imagine other images that would truly be rated as scary that you could have done or could do in the future?
I don't know. The reason I chose the faces was for 2 reasons. The face itself, I didn't want to kind of play with loaded dice and actually introduce an image that was already scary, because I wanted it to truly progress to a scary image. So I chose something that was relatively innocuous, just a face. And I chose a face because it has been shown that you have the grotesque reaction and you also have the uncanny valley reaction. And so I was hoping to play on those 2 factors when this face was shown. So I'm not too sure what other images. I definitely want to explore, and if I could create something more powerful and maybe pair it with a neural net, I would try to make it out of nothing, kind of like how the Google Dream does, just kind of like ta-da, scary image, but out of static noise. But I had to start somewhere in the middle ground. not too scary, actually cohesive. Does that answer your question? Any other questions?
All right, thank you, Charlie.
Thank you.